is Dr. S.P. Arsa from Mechanical and Engineering Department, IIT Roorkee. I am going to deliver my lecture 28 of the course of the strength of materials, and this course is developed under the National Program on Technological Enhanced Learning NPTEL. Prior to start this lecture 28, actually I would like to refresh your the concept of the previous lecture, in which we discussed mainly about if we have a beam and like if it is under the consideration of bending moment, then what will happen is means when the bending moment is applied, then what exactly the relations were there, that part we discussed. So I would like to refresh those things, because you see in that lecture we are going to discuss mainly on the numerical problems based on the previous formula which we derived, and also you see we would like to discuss about the shear stresses in this lecture. So you see in the previous lecture, if you just remind, then you will find that we had a beam is there, you see, and when this is under the consideration of or under the application of the bending moment M, only pure bending moment, there is no other forces are there, then you see like a simple bending equations which we derived, that sigma by y is equals to m by I is equals to E by R, in which sigma was the bending stresses which are inducing due to the application of this bending moment. So sigma by y is the distance, you see, on which we just want to find it out the bending stresses, and that fiber is having a distance from the neutral axis y. So this y is the distance from the neutral axis of that particular fiber. So sigma by y is equals to m by I. M was, you see, like the bending moment which is the applied bending moment, and due to that the bending stresses are coming sigma. And then m by I was there. So I was, you see, this second moment of area was there, which we defined the new term, which was nothing but equals to summation of y square dA. So there were, you see, the two main theories which we described to calculate this I. That was this second moment of area, because it has the summation of y square dA, the y square term is there. That's what you see we defined that as the second moment of area. So you see by integrating, if you have a regular structure, then this tapered bar or any the shaft or that kind of thing, then it's pretty easy to find it out by integration of y square dA. Or if you have different kind of sections, then you see summation of y square dA will give you this second moment of area. Then you see the third term is sigma by y is equals to m by I is equals to f this E by R. So E is the Young's modulus of elasticity and R is the curvature radius. So you see this is a simple bending the moment equation is there, and if you see this equation, then you will find that only the pure bending is there, there is no shearing part is there, there is no other stress components are there, only these stress component due to the bending is there in this particular equation. And you see due to that we can also find it out the maximum bending stresses, the sigma maximum, which is nothing but equals to, you see we discussed that this m by I into the y maximum distance. So m and I are the applied part. So this is maximum bending, this bending moment is applied, and I is the second this moment of area is there. So it can be easily calculated with the using of the dimensional one and the applied one. But the key feature is that actually what is the location is there at which this maximum bending stresses are coming, that part we discussed on that. And also we discussed that actually m is equals to z times this sigma maximum. So z was the section modulus, and it can be easily calculated based on, you see, m by I, because you see the section modulus is absolutely depends on that what is the exact structure is there of that kind of in which we want to find it out the maximum bending moment with corresponding to the maximum bending stresses. So that part, you see, we discussed in the first section of those things. And then you see other section which came up with that, you see, if we have a bending moment in that, or if we have a bending these this second moment of area is there on the neutral axis, then also we can calculate the any other this second moment of area at any section or any axis is using perpendicular theory and using parallel theory. So in perpendicular theory we described that if we are using the perpendicular axis, then the polar moment of section, that means, you see, if we are taking an area and you see these two axes on which we want to find it out the section area Ix and Iy, we can simply make the relations, the polar section of this inertia with this, because the polar section of inertia, or we can see this j is perpendicular to the area concerned, and this Ix and Iy are the two corresponding axes, this moment of inertia. So with that, you see if we want to relate those things using the this perpendicular axes, we calculated that z is equals to Ix plus Iy. So we can calculate that one. And And another relation which we describe using one theorem, that was the parallel axis theorem. So that was, you see, like it's pretty easy that if you want to find it out at any axis, let us say z axis, so Iz is equals to Ix plus integration of this this y into dA, or we can say that this we describe that h distance was there, so h square into a. So meaning is pretty simple, that we can calculate this second moment of area or the moment of inertia for any section once you know this moment of inertia for the axis which is passing from the centroid, or we can say the neutral axis. So these theorems which we discussed, and also we find it out that actually if we have a circular section or if we have a rectangular section, then also we can calculate those things. So for rectangular section which has this height is d and breadth is b, so we, for that you see we calculated the INA, that means you see the moment of inertia at this neutral axis is nothing but equals to BD cube by 12, or also you see if we have the uniform, the diameter from 0 to d, then we have, you see, I is equals to BD cube by 3. So this kind of discussion, like a derivation which we described. So in this lecture, you see, we are going to use again the similar kind of like the formula for that. And then the last section of the previous lecture which we described, that if we have like a big blocks are there in which the bricks are to be settled, and there is like the small the gaps are there in between those things to for setting up any fillers. For that kind of structure, like we can calculate this INA for like the bigger portion and the shaded portion. So I is the total, INA is nothing but equals to I for total rectangle section minus I is the shaded portion. So while comparing those things, we can calculate BD cube by 12 minus 2 times of, because you see the two different bricks were there, if you remember, 2 times of BD cube by 12, or we can say BD cube by 6. So you see here these kind of discussions which we made, but in those discussions you see there was no stress component due to the shear. So in this lecture, you see, first we will discuss about like that what will happen when like all these like the shear stress component is there. That is the second part, but first part is focused on whatever we discussed in the previous lecture, the formulae for the bending stresses and the bending moment we are going to use like for the numerical problem. So here you see the first numerical problem is that we have a I section girder. So we have, you see, the girder for the basis of any building. You see, you will find that on the top of roof, you see the girder is there which has the dimension of 200 millimeter wide by 300 millimeter depth flange. So one is the flange which has this diameter, and the web in between the web, it has the the thickness is 20 millimeter is used to simply supported beam for a span of 7 meters. So you see here for flanges, both of the flanges, you see the dimensions are 200 millimeter wide by 300 millimeter depth, and there you see the web thickness is 20 millimeter is given for the total span of beam is 7 meter. The girder carries a distributed load of say 5 kilonewton. So you see per meter. So you see here the load distribution is given on that particular girder which has the intensity of 5 kilonewton per meter, and the concentrated load, that means you see we have a combined load here. So one is the UDL in which 5 kilonewton per meter is there and distributed load is there, and other one is the concentrated load, or we can say the point load, that is the 20 kilonewton at the mid span. So this is the configuration of the problem. Now our main intention is to find it out the second moment of area of the cross section of the girder, because it is the I cross section is there. So for that we need to find it out, and also we want to find it out the maximum shear stresses, maximum stresses which are being set up due to this load application, the combined, the UDL as well as the concentrated load. So for that, you see here the second moment of area of the cross section can easily be described when you see we know the total regular structure. So for that simple we have taken the section with the symmetricity about the neutral axis can be easily made if we have the I section. So for that, you see since it is a I, so centroid is absolutely passing from the rectangular section of the mid portion of this I, which has, you see the total, this I is nothing but equals to BD cube by 12, which we have described for the rectangular section. And here you see it's a this middle portion of the web, I should say, is a rectangular portion. So we can simply get those things BD cube by 12. And the section can this be divided into convenient rectangles, because you see these are all the rectangles for each of which the neutral axis passes through the centroid, because it is a well balanced structure. So all the neutral axis is just passing from the centroid of those I section. Example, like in the case enclosing by girder is just by a rectangular. So you see whatever description is there of this kind of problem, it is absolutely based on the I section. In the I section, you see this neutral axis is just passing from this particular centroid, and you see, like it has a symmetricity all along both of the side, you see. So we can say that whatever the things will, like analyzing for one section, it has a symmetricity on the other section also. So for that you can see this particular diagram. So in that, what is that, you see here, this is the I section, you see, and this is the web part, and this is I section. So I am, like just go with my cursor, you will find the I structure here. So this is the I structure here, you see these two, this is one flange, this is another flange, and this is the web part. So you see here, like as it is being, like discussed here, that this is the 300 millimeter of this, and this is the 200 millimeter, and 20 millimeter the this web is there. So this distance is 90 and 90, so total is 180, and this is 20, so this is 200. So just keep this thing in your mind that this is the I section, and the neutral axis is just passing from these. As I told you, it has a symmetricity on both of the side. So for that we can simply calculate the I girder, which is nothing but equals to I rectangular, the total rectangular part, like minus I shaded area. If you remove this shaded area, then you have the I section. So for that, you see, like if you are talking about the total rectangular area of this, then you what we have 200 into 300. So 200 into 300 cube divided BD cube by 12. So B into D cube by 12. So this is there into 10 to the power minus 12, because it is in the millimeter. So we just want to calculate in the meter side. So we have this one minus 2 times, because these two shaded areas are there. So 2 times into 90, 90 is this, as I told you, because this is the 20. So 90, 90 and 20, the total 200. So that's what 90 into 260, as it is given, you see, like this is 260 for this description. So 260 divide cube, so BD cube divided by 12 into 10 to the power minus cube. So now if you analyze those things by that, then you have 1.86 into 10 to the power minus 4 meter 4. So now you see here, since I section is a well symmetrical section all along these two flanges and one web, so it's pretty easy to calculate, you see, with the using of this. First you calculate for a entire rectangle, and then like reduce the shaded portion out of that. So you will be ending up with this kind of structure, and the maximum stress may be found from like the simple bending theory of equation. As you see, we discussed in the previous case that sigma by y is equals to m by I is equals to E by R, or we can say that if you want to find it out the maximum bending stresses, then it is nothing but equals to the maximum bending moment m by I into y maximum. So for that, you see, like it's pretty easy to put those values and get the final thing, because you see here there are two different kind of loading is there. So first of all, our main focus is to find out the this bending moment. So for that, you see here the two main loading, as I told you, one is the UDL is there, which has like the intensity of 5 kilonewton per meter, and then we have a concentrated load like of some magnitude. So in order to obtain the maximum bending moment, the technique will be like consider each loading on a beam separately and get the bending. Like we need to just go with the separate kind of loading and get the bending moment due to like due to these loading, as if no other force is acting on the structure, and then you like superimpose of these two results, because you see first the UDL is there and then the concentrated load is there. So we need to calculate the different segment and then combine it, because our main focus is that there is no shearing is occur on that, only these bending stresses are there due to this bending moment. So that's why you see we need to like compute these like bending moment or bending stresses very carefully along with this particular kind of load. That's why you see like the maximum bending moment is nothing but equals to WL by 4 plus WL square by 8. WL by 4 is coming due to this point load, or we can say the concentrated load, plus you see whatever the bending moment is coming due to the UDL. So this distributed load WL square by 8 is there. So if we are keeping those things, then we have this W, which is 20 kilonewtons, or 20 to 10 to the power this cube. So that is in like the Newton, this are in kilonewton. Then we have the L, that is the 7 meter divided by 4, plus W, which has you see the 5 kilonewton per meter. So 5 into this 10 to the power cube into 7 square, because the total length of the beam is 7. So 7 square divided by 8. So if you compute, then we have the maximum bending moment is 65.63 kilonewton meter. Once we have these things, then we can pretty easy easily calculate that what will be the maximum bending stresses, and for that you see the sigma maximum is nothing but equals to m maximum divided by I into y maximum, or if you are keeping those values 65.63 into 10 to the power cube. So this is you see the maximum bending moment which we calculated on the above side, into you see now you see like we want to find it out at this 150 this millimeter from that side, 150 meter from that side. So you see here we are keeping those things, and I, you see, we just calculated 1.06 into 10 to the power minus 4. So we are keeping for this value for this I section which we calculated. So if you are putting all those values, then we have Y maximum is 51.8 mega Newton per meter square. So you see, this is the exact procedure to calculate. First of all, what is the I? Because you see, the second moment of area is very important for any kind of structure, that what exactly the cross section is. Here we have just chosen the cross section of the beam is I section. So that's why you see, we have, first of all, we need to obtain that part, and then you see, what will be the maximum bending moment is there. So it comes that it comes only due to that what kind of loading is there. So once you know the loading or combination of loading, then again segregate those part and calculate the combined effect of those things. So we have, you see, the maximum bending moment here. Once you have the bending moment, once you have, you see, the second moment of area, then it's pretty easy to calculate the maximum bending stresses by using the simple bending equation theory. So you see here these values are. So again, you see, all these things, it can be easily predictable for these kind of examples. So you see here we have an example that if we have, the simply supported beam, obviously the UDL is there. So one is the UDL which has the intensity of 5 kilonewton meter, as we discussed in the previous case. And you see this at the mid of the span, what we have the 20 kilonewton of the point load. And you see, this distance from this, because the total distance is 7 meter. So at the center point we have the 3.5 meter. So with that, now first of all, our main intention is to combine those loading, because you see here we have the UDL as well as we have the point load. So with the combination of those things, as I told you, see, the maximum bending moment is coming by WL by 4 or WL square by 8. So with that, you see here we simply combine those loads here, with the UDL plus these things, and then you see the reaction forces are coming out of those things. And then once we have the reaction forces, you see, we can go for the shear force diagram and the bending moment diagram also as well, you see, because here if you go for these reactions here, all these, the joint points, this reaction points is just going on the top of side, this is, you see, just going on the bottom of side. So we have, you see, this positive direction here, and if you go for this right hand direction, this reaction is going on the top of side, this is going on the bottom of side. So you see here we have the negative directions, and you see in between there is a point load is there which will give you an abrupt change in the shear force. So just with that concept, you see, we can simply draw on the shear force diagram. So this is, you see, at this particular point, you see, we have the maximum this shear force due to the reaction, and then it is just going reducing here up to this point, and then there is a 20 kilonewton, the force is there which is on the downward direction. So there is, the change is there in the shear force, and then there is a negative direction because of the sign convention. So we can calculate those things pretty easily. Now you see, because as I told you, this is pretty simple to calculate. We can again segregate into two parts, as we discussed in the previous case. You see here that first just go with the UDL. So this is, you see, the first case with the UDL only. Okay, so in this 5 kilonewton per meter is there, okay, and the 7 meter is the total length. For that, this CFD is there, as we discussed in the previous cases, you see, and this is the bending moment diagram. And then you see here, this is one part. Another part is that this beam is influenced by also this 20 kilonewton. So this is a simply supported beam. Point load is there at the mid of the span. So for that, you see, this W is coming, and then since it is segregating into exact equal part, so we have one positive, one negative part in the shear force diagram. So this is the positive and the negative part, and since there is no UDL is there, so simple triangle is coming because of the point load. So now you see, if we combine those things, then you see it is a very important thing that once you combine both of the things, then you have we are ending up with those things. So you see here, this is the combination, the maximum, these things are there, then it is decreasing, this decreasing, and you see up to that point it is decreasing. So you see up to this, it is bisecting here, it is also bisecting here. So this, you see, the changing area is there. So it is very interesting, if you want to calculate those things, then just on the top of that, you can see that this is the real problem, our problem, equating to one problem by this UDL plus one problem by point load. So you see here we can simply analyze those things, or in the bending moment, if you go for the previous slide, then you will find that the maximum bending moment was WL by 4 due to this point load 20 kilonewton plus WL square by 8 due to this UDL of 5 kilonewton per meter, and we can calculate those things. So, you see here we have the shear force diagram for both of things and we have the bending moment diagram for both of the cases. So, you see here in these cases, you see we only focused on the bending moment as well as the bending stresses which are coming due to like these applied moments at this particular beam, in irrespective whether it is a cantilever beam or a simply supported beam. Now, you see here the main key feature of this particular lecture is to focus on the shearing stresses in the beam, and all of the theory which has been discussed earlier, as I told you, just on the bending stresses in the beam, like for any kind of a pure bending is there, that means a constant bending moment is just acting along the entire length of the beam. Now, you see here we would like to focus that we have a beam just let us say AB beam is there which is transversely loaded and then you see with that we have a kind of forces which just creating the shearing. So, together with the shearing force and the bending moment, we can simply notate that the middle portion CD of the beam is free from the shear force, and that you see the bending moment is always load into the whatever the distance is there at which the load is acting, P into A is always uniform between these two particular section, and that is why you see we are always saying that whenever the pure bending is there, always gives you by the bending moment which is applied to the both of the section. So, you see here since when we know that these point loads are coming along with this particular section in which I just told you that you see here the constant shear forces are there for which there is no the bending the dm by dx is 0 since there is no shearing is there. So, for that the bending moment is constant. So, you see here when we are talking about those things, this is a pretty simple diagram or which the 2 point loads are there, both are just going downward direction, the reactions are coming from this which is on upward direction. So, if you are going for the bending moment, then you will find that this and this direction you see on the left hand portion. So, we have the positive shear force. So, this is the positive shear force and this is the negative shear force, but there is no load application in between. So, there is no shearing is there or there is no resultant shear forces are existing in between these section. So, when we have no shearing force, so F is equals to dm by dx. If you are keeping F equals to 0, dm by dx is equals to 0, that means M is constant. When M is constant, that means only bending moment is applied on a beam, and this is the main condition of the pure bending. When you see only the bending moment is applied, the the total stresses which are inducing in this particular beam is just the bending stresses due to this M. So, you can visualize this thing in a this bending moment diagram. So, this bending moment is P into A, as we discussed, M is equals to P into A, and which has a constant value of this particular section, and these things are there due to the shear forces. So, this is you see one of the example in which we can say that there is a condition in which the pure bending is there, but it is also computing with certain kinds of this shearing stresses. So, our main focus is just to focus on that actually if we have this kind of loading, then how we can conclude the shearing altogether with the bending stresses. So, conclusion is hence one of the conclusion which is coming from the pure bending theory was the shear force at each cross section is 0, because you see only the pure bending is coming, there is no shearing is there, and the normal stresses are due to this bending are there only, which are producing on the top of the fiber we have the tensile stresses, on the bottom of the fiber we have the compressive stresses. So, these flexural stresses or we can say these normal stresses are always coming, but there is no shear stresses are there. In that case, you see the non-uniform bending of a beam where the bending moment varies from one cross section to another, there is a shearing force on each of the cross section and shearing stresses are also be inducing in the material. That means, you see whenever a non-uniform the bending is there, if it is a uniform bending, there is no point to go with any kind of shearing, any kind of twisting or any kind of couple is there. But whenever the non-uniform bending is there, always it gives you for different cross section a different kind of shearing forces are there and corresponding shearing stresses are there in the material. The deformation associated with the shearing stresses causes wrapping, you see, because you see whatever the deformations are coming, they always causes the wrapping of the cross section, so that the assumption which we assumed while deriving the relation for this plane cross section after bending remains plane will be violated, because you see after once it is wrapping, once it is deviating from the original the position, then we can't say that you see once you remove the load it will be in the main form of all those fibers, it won't be possible. So, for that you see this assumption is violated, that means this condition, whatever the condition sigma by y of sigma by y equals to m by I equals to E by R is absolutely violated for this kind of relations. Now, due to the wrapping, the plane cross section before bending do not remain the plane after the bending, as we told you, and this this complicates the problem, but more we can say elaborated analysis shows that the normal stresses due to the bending as calculated by a simple equations like sigma by y is equals to m by I equals to E by R, and this equation gives the distribution of the stresses which are normal to the cross section that is in the cross section, or we can say along the span of a beam are not greatly alerted because by the presence of these shearing stresses. Thus, you see it is justifiable to use the theory of pure bending in case of non-uniform bending, and it is accepted in practices also to do these things. That means you see sometimes when we know that the non-uniform bending stresses are also be there in those cross sections, then also we can apply these normal stress concept that okay, these the normal stresses are there along with that particular fibers, on top of the fibers we have the tensile stresses, on the bottom of the fibers we have this kind of the compressive stresses, and we have a neutral axis. So, we can apply all these this perpendicular axis theorem or this parallel axis theorem for those things, and also we can apply this equation sigma by y is equals to m by I equals to E by R. So, that is a justified case is there for this kind of theory in which you see the non-uniform bending is there, and we can say that whenever a pure bending is there, it is just due to this particular M concept. Now, you see here, so in that you see we just focused on the uniform or non-uniform bending. Now, our focus is that the shear stresses are there in the beam. So, by the earlier discussion which we discussed, that we found that only the bending moment represent the resultant of a certain linear distribution of the normal stresses sigma x or the cross section, that you see the upper fibers are there with the tensile stresses which is one form of the normal stress, and lower fibers are there of the compressive stresses which is also one form of the normal stresses. Similarly, the shear forces Fx over any cross section must be resultant of a certain distribution of a shear stresses, because you see whenever the shearing is there, whenever the kind of twisting is there, always it induces some sort of the shearing stresses, and these stresses are always coming with along with this particular bending stresses, and our main focus is on that only. So, you can see here this particular diagram, as we discussed, we have a simple structure of a particular kind of a straight beam in which this cross section is like that, and on that particular we have this particular section influenced by shearing force. On the top of that, this cross section after this the delta x segment, we have the cross section at this particular shearing forces are F plus delta F, and then you see we have the bending moment which is in the sagging form. So, M, and this is at this particular side after this delta x we have M plus dm. So, with that our main focus is that that what will happen along with the neutral axis and on above. So, this is the neutral axis over which you see our main this plane of the matter of the this main plane is concerning, and over which our main focus is coming on this particular way. So, that what will happen and how these fibers will react due to this F and this F plus this F plus delta F along with this way, or we can say in sagging form that M on this particular way and M plus dm will act. So, if you see those things, then you will find that the resultant stresses are coming, because you see here not only the bending stresses are there, but along with this we have the shearing stresses. So, that means you see whatever these things are coming, these are coming with the resultant part. So, we have the resultant stresses of this particular thing. So, these resultant stresses are there, and you can see here they are coming in the triangular form at this particular point, and at this particular point the triangular form. So, we can say that the resultant stresses, this sigma at this point, and here it is sigma plus delta sigma along with this point, and this side just to be compared with the other side, in the sense that this small element is in the equilibrium position under the action of the shearing force as well as the bending moment. So, we need to concern that you see when it is coming along with this x and y axis. So, what are the stress components along the x axis, what are the stress component along the y axis, and how this twisting will take place, and due to this twisting and shearing forces what kind of interactions are there. So, now If you focus on this element, let us say the y distance is there from this neutral axis, and we have, you see, the AB element. So, now you see of this fiber, our main focus is that now if you are taking a small element dA, you can see this particular part. So, we have a small element over which the stresses are acting. So, when the stresses are acting, you see here our just the clear cut, like the description is there that it has the area dA is there, which has a distance from, like the neutral axis y, and the section modulus is z is there for this kind of thing. So, now with this particular width of the cross section and with this dA area of this small element and with these stress components, you see from the left hand side the sigma, from right hand side the sigma plus delta sigma, and under all these forces, the shearing forces and this sagging the moments, this object is in the equilibrium portion. So, now our main analysis will come that what will be the resultant bending stresses are there and what will be the resultant shearing stresses are there. To calculate those, you see, and to put the the relation in between those things, certain assumptions are always needed because of to avoid the complication in the system. So, for that, you see, first of all, the first assumption is that stress is uniform all across the width of those things. That means, you see, it should be parallel to the neutral axis. If it is not parallel, then you see, the fibers are playing in the different way, and then you see whatever the stresses are coming on the fibers due to these combination of the shear stresses and the bending moment, altogether it is different. So, that is why you see, first of all, the first assumption is very important, that whatever the stresses are occurring or inducing in this particular beam, it has to be uniform all across the width. That means, you see, they have to be parallel, just parallel to the neutral axis. This is one. The second is the presence of the shear stress does not affect the distribution of the normal stresses. That means, you see, since we have the shear stress presence is there, and along with that there is also this bending moment is there, and due to that the bending stresses are there, but whatever the presence of the shear stresses are there, they will not affect in any way to the distribution of the normal bending stresses. So, normal bending stresses are always coming as per its own concept. That is what we can again apply the same theory, the sigma by y, which is equals to m by I is equals to E by R in this equation also. And it may be noted that the assumption number 2 cannot be rigidly true. Sometimes, you see, as an existence of shear stresses will cause a distortion of the transverse plane, and that is what you see, which will not be exactly there with the same plane. That means, you see, once we apply, once we remove the load, it will not be exactly in the same plane before and after bending. So, this sometimes this assumption 2 will not be valid for certain cases, but in general cases we can agreed upon those things that okay, these are valid for certain things. And in the above, you see, all those figure which we described in the previous one, that we have a simple segment and we cut the one portion over which one portion is affected, one side is affected by sigma and one side is affected by sigma plus delta sigma. So, for those, you see, for that the two main transverse sections are there which we concerned, which has a distance of delta x apart from one point to another point, and the shearing forces and the bending moment, as we discussed, they are at one point it is F in this direction, and another point we have F plus dF in this particular direction, and then you see we have the bending moment also at one point it is M which is going in this direction and M plus dM which is going in this direction. So, we both of the sides are being influenced by both shear forces as well as the bending moment in that. Now, due to the shear stresses on the transverse plane, there will be a complementary shear stresses are always be there on the longitudinal planes parallel to the neutral axis, just to balance the equation. Otherwise, you see what will happen if because of these shear forces and because of these things, the bending moment, the sagging moment, bending moment, we cannot get exact equilibrium position, because if for any analysis this is a must condition that the equilibrium position must be coming within those things, and then only we can apply all those equations. So, for that, you see, there is a complementary shear stresses are there just to balance these the shear stresses acting. So, the counter the shear stresses, or we can say the complementary shear stresses, are always there on the longitudinal planes, they are which are just parallel to the neutral axis, and they will form always, you see, just to balance these equations. And if I am saying that the tau is the value of the complementary shear stresses which are coming in the transverse shear stresses at and let us say a distance of y0 from the neutral axis z, then from the neutral axis, then we can say that there is one more component which has to be defined, which is the z, which is nothing but equals to the width of the cross section at any position. So, now you see we have the two dimensional parameter. One is where the tau is acting, that means you see where the complementary shear stresses are acting, that is at the distance of y0, and another one is from the neutral axis, and another one is the width of the cross, this width is there of any cross section, and which we are defining by the z, and like it is absolutely based on what kind of the cross section which we are using. So the z value is varying. A is the area, as I told you, in the cross section cut off by the line parallel to the neutral axis, and y bar is the distance of the centroid of the area from the neutral axis. So we found that these are some of the geometrical parameters which can be analyzed for any kind of numerical problems while we are dealing with those things. So here this tau, which we found that the complementary shear stresses are there, which are always inducing in that kind of structure whenever even the shear forces are there, or we can say that these bending moments are there for that kind of thing. So here with those the components, as we discussed for this left hand side and right hand side for this this small element, again we found that the sigma and sigma plus delta sigma, which is the resultant stresses are there due to the shear force and the bending moment, are just normal stresses on the element on the area dA at the two transverse section, as we shown in the previous diagram. And then you see, if we want to find it out the difference of the longitudinal forces, on one side we have the force sigma into dA, on another side we have the force of sigma plus delta sigma into dA. So if we want to find it out the differences of the longitudinal forces, which is always be equal to delta sigma into delta dA for that small element. And you see here we just want to find out this quantity, this d sigma into dA is the quantity which is summed over the entire area. This area A is in equilibrium with the transverse shear stress tau on the longitudinal plane of area which has the z into dx. That means you see our main focus is just that how these stresses are being set up. And one side you see we have of this, because our total area this thickness which we have assumed is delta x. So at one side we have this sigma, at one side we have sigma plus delta sigma, and then you see what will be the total the resultant longitudinal forces are there, which is being set up due to the these shear forces as well as the bending moment. So that's why you see it is coming like that. And then after focusing on those things, what we have this tau z into delta x, which is the resultant part is there, the longitudinal forces. So tau, which is coming due to the complementary shear stresses, delta is the width, the z is the width is there, and dx, which is the total thickness which we are assuming. So this tau, which is stress into this area, will give you the force, which is equals to the integration of d delta into dA, because you see these are the longitudinal transverse forces are coming due to the resultant force. The difference is there. So if you integrate for entire region, then you will be ending up with the integration of d delta into dA. So from that particular bending theory, again we can simply apply the sigma by y, which is equals to m by I. So from that we have the bending stresses sigma, which is nothing but equals to m into y divided by I. So, or we can say that since this is on the first section, on the second section you see we have sigma plus d sigma, this is the total stresses on the other side, and due to that we have the bending which is coming on the sagging way, m plus delta m into y divided by I. So from those above two equations we can conclude that the d sigma is nothing but equals to delta m into y divided by I. So here you see we have the shear stresses tau into z into delta x is equals to integration of d sigma into dA, and we have you see the total the another stress formula, this d sigma, which is nothing but equals to delta m into y divided by I. So if you compare both of the equations, then you will find that these stresses are the resultant stresses coming due to the shear part, the shear forces, that is the tau is there one figure, and due to the bending moment delta m is there. That means you see whatever the normal and the shear stresses are coming, they are the resultant part due to these two portions. So you can again visualize those equations from this particular figure, and this figure says that you see we have a small rectangular section, this this cross section, and the total this length is delta x, and for that you see this neutral axis passing from this, and this is our main strip of or which our main focus is that how the stresses will play. So on one side of that we have sigma into dA, and on another side we have sigma plus del sigma into del A. So you see here how they will balance. So exactly, you see we discussed in this particular section that on this is there, and then we have the distances from like the neutral axis of this particular area, that is the y distance is there, and this y0 is the initial like the distance is there, or we can say y bar is there that we define, for which you see this I x is there, is nothing but equals to integration of y square dA. So for that, you see like along with those neutral axis and along with this particular axis, since both are you see like coming all together like with the same way, and there is a combined effect is there of the shear stresses as well as like the shear forces as well as the bending moment. So we can simply visualize that actually when these fibers are being influenced by both of the way, then the resultant is coming from this side sigma into dA, that is the force is there, and on this side sigma plus delta sigma into dA from both sides. So the resultant, since, and we are saying that this small element is in equilibrium position along with this particular like whatever the forces are coming, so they will like cancel each other, and that's why you see the complementary shear stresses are also coming, the tau, which are there all across the parallel to like this cross section, or we can say that the parallel to the fibers, and that's what you see like we assume in the previous section. So here if we substitute those things which we got, the d sigma is delta m into y by I, and from the second equation by like the basic bending this equation, and the second part you see the first thing was there due to this tau into z into delta x, which is equals to like this integration of this d sigma into dA. So now if I replace this d sigma here, then what we have the tau into z into dx is equals to integration of delta m into y divided by A into delta A. So now you see here like if you consider this particular equation, then you will find that we have both of the component, we have the shear stress component, we have the bending component, and due to that you see like the resultant is coming. So if you analyze those things, then dm by I is simply taken out, and we have you see this tau into z into dx is equals to delta m by I integration of y into dA. Or you see like just go to the main relation between the shear force and the bending moment, we have the shear force F is equals to dm by dx. So with that you see like again we can simply put those things here. So by keeping those values here, this F is equals to dm by dx, we are ending up with the tau which is equals to F, the shear force is there, divided by I into Z, because this Z will come, the delta, this delta m and delta x will be giving you the F. So the F will come here, I into Z integration of y into dA. But from the definition of integration of y into dA, as we discussed in the previous section, which is equals to A times of y bar. Again you see this y integration of y into dA is nothing but the first moment of area, because you see in the previous section we discussed about the second moment of inertia, that is the integration of y square into dA, and the second moment of inertia will give you the real bending feeling. And here you see like we have the first moment of area, that is the integration of y into dA of the particular like the shaded portion which is there, and the y dash is, as I just told you in the previous diagram, that it is nothing but just the location of the centroid from the neutral axis. So you see how much distance is there of the like the centroid from this neutral axis. If they are common, then you see like this particular first moment of area, it is just like coincide with each other, and we can calculate correspondingly. But here you see whatever the distance is there of the y bar which has like the main distance from the centroid to neutral axis always coming up in the corporation of this first moment of area. So with that you see like we can simply put this A into y bar here. So we are ending up with the shear stress formula. Shear stress is nothing but equal to shear force F into the total area A into y bar, which has the distance of the centroid from the neutral axis, divided by I into Z, where Z is the actual width of the section at which the position like at any position is there, and the tau is like this complementary shear stresses are there which can be easily calculated, and I is the total moment of inertia about the neutral axis. So now you see if you focus on this formula, then the shear stresses mainly like is coming due to the shear forces, that what are the shear forces are there, in what direction these shear forces are there, and you see what is the affected area under which these like the shear forces are acting. And then you see again the key feature is that what is the exact distance is there of the centroid from the neutral axis, and then like this total moment of inertia I is a key feature, because what kind of the cross section which we are taking, correspondingly you see like the shear stresses are coming, and then another part is like what will be the total width is there of the cross section. So the dimensional parameter of the cross section is very important to visualize the shear stresses in those things. So now we would like to conclude this chapter. So like in the first section of this chapter we discussed about when a beam is under the combined load, then how we can calculate like the bending moment as well as the like the bending stresses. So in that you see we found that if the UDL is there and the point load is there, then how we can segregate both the issues, and then you see we need to calculate like the different for the different sections the maximum bending moment, like you see like in case of point load we found that WL by 4 is there, in case of like the this UDL WL square by 8 is there, and then we can calculate the maximum like the shearing stresses, that is like this M by M maximum divided by I into this Y maximum. So like this kind of situation it's pretty easy to analyze. And then in the middle portion you see our main focus was there that whenever a beam is under the action of like the shear force as well as the bending moment, then the main assumption of this bending, like once you remove the load you see like, or once you remove this bending moment, then the situation is exactly same as the previous. That means you see like the fibers are having the same kind of plane of the section as before and after the bending. So in the whenever the shear forces are acting, then this situation will not remain exactly as the previous case. So that's what you see, this theory is sometimes the uniform and non-uniform bending. In non-uniform bending sometimes it is not valid, but like it depends on what kind of structure which we are using. Based on that you see this sigma by Y is equals to like M by I equals to E by R, is it can be valid for uniform and the non-uniform bending part. And then in the final part you see we discussed about the shearing stresses of a beam. In this like some of the assumptions which we made, that whenever you see the forces are applying on this particular like the beam, then how we can like put the cross section of this particular beam, and how we can analyze for the shearing forces. So these two assumptions sometimes like it is valid, sometimes depends on what kind of structures or cross sections which we are using, these assumptions are valid. And then like in the last section of this we found that the shearing stresses are always you see like they are the resultant stresses coming due to the shear force as well as the bending moment. And like if you want to calculate the shearing stresses, then it has like the total component of the shear force F into area into Y bar, which which is the distance of the centroid from the neutral axis, divided by I, which is like this total moment of inertia into the total whatever the actual width is there of the cross section. So in that in the any shearing force, the shearing stresses if you want to calculate, it is highly sensitive to first of all that what is the cross section of your like the object is. That means you see whatever the beam which we are taking, what exactly the cross section is. And then the second thing which is very important, that how we are like configuring those things, means actually how, like if you are talking about I section or if you are talking about the rectangular section, then what is our affected area on which our main this study is. So based on that you see like we can simply calculate the shearing stresses, we can calculate the bending stresses. This is sigma, which is nothing but equals to sigma by Y is equals to M by I or equals to E by R. So based on either that equation or this equation tau, which is F A Y bar divided by I Z, we can simply calculate the bending stresses and the shearing stresses for a beam which is under the influence of shear force and the bending moment. So you see here this in this section we simply like go with the simple assumptions, and we simply put certain the shearing stress equation and the bending moment equations for bending stress equations. In the next chapter you see our main focus is that if we have the different sections, as I discussed, like if we have a circular cross section, or if I have a this I section, or if I have a rectangular cross section, then how can one can be calculated you see this shear stresses and the bending stresses for that. And which you see if I am just taking like this I section or any section, then which of the area is having like the maximum this shear stress or the bending stresses, and then how this interaction is there like this bending stress and shearing stresses, and what is the real relation is there in between those stresses. These are our main matter of concern, and that part you see we are going to discuss about the different kind of cross section of a beam. Thank you. you.